So welcome to the part 2 of this 3-part workshop series. For part 2, we will be learning how to the necessary materials to perform molecular dynamic simulation, and also running the simulation and some basic analysis. Okay, for this part, you're going to have to install Windows System for Linux. So you'll be looking at something like this. Hold on shift. If you hold on shift, you can open a Linux shell here option on your Windows 10 or Windows 11. So watch that video, learn how to install the Windows System for Linux, and then you can continue with this workshop. Okay, so assuming you have done the Windows Subsystem for Linux installation, let us begin from where we left off. So we're going to first install the VMD, a very necessary software. So if you can Google it to download, but if you have downloaded the software from the Google Drive, you can open it from the folder. So it's this one. Okay, for this process, you can simply click next. Okay, I'm not going to continue with the installation for myself because I've installed it. For you, go on and proceed to finish the installation. We've installed VMD. So now we're going to add VMD to the path. So we're going to open the Windows search box and type Advanced System Settings. This one. Then we'll click on the environment variables. And under system variables, we find path, which is this one. And then we click on edit. So from the edit environment variable, we're going to find where our program is installed. So it should be here, and so I find VMD. Yep, there it is. Open the VMD folder until you reach the point where there's vmd.exe. So the path is this one. This is the path. C program files VMD. So we're going to copy that, Control C, and then go back to our settings. And then we're going to click it here. We're going to click new and paste it here. Then we're going to click OK. Click OK again, and OK again. And we're going to test run. For example, we go back to our Bioinfo workshop. And then we're going to hold down the shift key and right click. And then we're going to open a PowerShell window. Then from PowerShell, type in VMD. You should be able to run VMD by just typing the VMD now. So that's good. So this is what you can see. This is the list of the version. So if you're using NVIDIA, you can use this version. This here, although it's written AMD, is actually using the version that uses CPU power, not the GPU. So yeah, so unfortunately NAMD is very much biased for NVIDIA. But moving on, so I'm going to show you how we are going to install NAMD. Okay, firstly, find the version that you want, download it or get it from the Bioinformatics Workshop folder, and move or copy that file into that folder. Okay, as practice. So this is my WSL work folder. I put it in desktop. So any softwares that you'll be using WSL, I'm going to put it here for ease of access. So let's see how we're going to install. So we put this here on this side, and here on this side. Right. So as you can see here, I have the NAMD 3.0 CUDA version because I'm using my computers are using NVIDIA. But this method is similar for all three versions. So this time we're going to use a Linux shell. Hold down Shift key, right click, open the Linux shell. Okay, wait for it to load. So from here, we can type in ls. It will show you all available, uh, all. It will show you all the available versions. Sorry, it will list all the files within this folder. I'm going to reinstall the NAMD so we all can do this together. So I'm going to install this version here, but we're starting from the tar.gz. So let's do that. We just use your left mouse key to highlight the version of your NAMD with the tar.gz. Control C to copy, and then you right click here. Oh, I almost forgot. By the way, you can press Control U to clear it. We should write a code here, tar.zxpf space, and then we right click. So this is a command for us to unpack the tar file. So once it's finished unpacking, it will look like this. If this kind of line appear, so it means the process is complete. So we can input new command. For now, we type in ls. We're going to change the directory into the NAMD 3.0 folder that we have unpacked. So it should be this one. Again, use your left mouse to highlight the desired folder. Ctrl C to copy, and type in cd for change directory, space, right click, enter. So now we change folder into the NAMD 3.0 software folder. Now we're going to write sudo sup for password, and then we're going to type in cp NAMD3 space /usr /local/bin. Okay, so everything should be okay now. So let's see if it works. Type in exit, and now let's try type in NAMD3. Okay, so if you receive this kind of message, means you have the NAMD running now. So don't worry about the fatal error. This is because NAMD require you to put a certain specific command for us to begin simulation. But for now, we've successfully installed NAMD. Sorry. So now we've got the NAMD3 and also VMD installed. So we now can begin with our NAMD simulation. So the steps are as follows. Firstly, we need to prepare our simulation files. We can use a website called CHARMM-GUI, and from there we're going to set up the simulation parameters using the CHARMM-GUI, and then we're going to download the prepared files and run the simulation. And I'm also going to show you how to resume and combine simulations, but prior to that we're going to learn how to running the post hoc analysis first, and then we're going to learn how to resume or recombine and resume our combining simulations. Okay, so now let's do the first bit here. So the instruction is like this. We're going to have to register to use the website. So when we registered, we go to the input generator, and depending on your protein, we're going to use a different builder. If our protein is not a membrane bound, is found in cytoplasm, we use a solution builder. If it is membrane bound, we'll be using a membrane builder. So our protein of interest is not membrane bound, so we can use a solution builder. Let's check. Let's try. Here, then we go for CHARMM-GUI. Here we're going to log. So you may be sure you log into your account here for you to use the builder. So we go for solution builder, and now firstly we ask for PDB file. So let's upload our complex protein. Okay, so this is our files that we have from Bioinformatics Workshop so far. We know from previous session that this one has the ligand bound position most similar to our reference template. So this one is likeliest to be the correct PYL ABA complex. So we're going to upload this one. Click on open. So we go click on open. Okay, so now just also be sure to check this one, check all correct PDB format. Click on next. Oh, okay, you see here, download PDB contains character not allowed in file name. This is a dash, so we need to correct our file name. So we go back to our Bioinfo workshop folder. We find the protein complex we want to use. Even better, let's just rename the whole thing so we can refer to them easy in future. Let's name it PYL underscore. Also, CHARMM-GUI cannot accept any spaces, so use underscore to create space. PYL ABA. Also, it's PYL 10 ABA complex, something like this. Okay, so let's upload that. Let's refresh that. Okay, PYL 10 ABA complex. So once it's uploaded, click next. Okay, so it scans for our file and identify protein. We give the protein segment ID pro A, and it gives the heteroatom, which is the monosaccharide acid. It gives the name het A. But because we're studying both the protein and the ligand, so we're going to check both. And then we're going to click next step, manipulate PDB. Depending on the complexity and the size of your protein, this can be long. So reading heterochain residues here, if you see this will not always happen, but if it shows, it means that the CHARMM-GUI cannot replicate the ligand structure properly. So it asks you for the reference file. So we're going to upload our ligand files that we have made, that we have downloaded and minimized on the previous bioinformatics tutorial session where we do the molecular docking. So it is in .fdf. So let's check. Click here to choose file. Okay, it should be this one, the ABA ligand 3D compound. Minimize. Okay. For the rest of it, you can leave them as they are, and then click on generate PDB. Okay, after that, under solution builder, it will ask us about the water bottle size. If you're using NAMD and we're using CHARMM topology, we can use octahedral, which is, from my personal experience, is much easier to work with compared to square box. And you can enter the edge distance. Edge distance refers to the size of system. So if you do from 10 to 20, it becomes 2 times bigger. You can change it to 5 to make it smaller, like so. The default is 10, and we can leave it as default 10, but sometimes if your protein is really big, it will cause error when you're running the simulation. So you can, to be safe, and change this to 20. There's no problem. It's just that the simulation that's going to happen will be longer. That's it. For now, for this tutorial, you just keep it at 10. It should be okay. And then from here, we can manipulate the system to add in potassium ion and chloride ions. This is default 0.15, and then we can, if you manipulate anything here, be sure to click calculate solvent composition to update. For example, if I make it 2 times bigger, the number is going to increase, right? Yes, I'm going to revert it back. Or perhaps maybe it's better for us to make it bigger just for the sake of experience. Okay, let's make it 15. Calculate solvent composition, and then click on next step, solve the molecules. So this is what we have done so far. We upload the complex file, have them checked. We've uploaded the ligand SDF file, and then we change the system to an octahedral, and then okay, this is what we're going to do next. Selecting the phosphate settings. If you're using NAMD, just use the default CHARMM-36M. We're going to check the WYF and hydrogen mass partitioning settings. If you have calcium ions in the system, there's an additional things that you can check as well. I will show you later. Input generation, keep it at NAMD. For the temperature, you can leave for default for 303.15 Kelvin for general system, but if you're doing something that within the human body system, you might want to use 310 Kelvin, and then you can download it. So now we've reached the force field options. So we can check these two. If your protein has calcium within the PDB structure, you can check this one as well. Mine doesn't. For our workshop, we do not have one, so we leave empty. And then input generation option, we're going to check on NAMD, and here we're going to leave it in VT ensemble and PT ensemble, and we leave the temperature at 003.15 Kelvin, and we click generate equilibration and dynamics input. Everything is complete. We can click on download. Right. We'll wait for it to compress, and we're going to download them into our bioinformatics workshop folder. Save as. Right. So let's give a name, PYL10. Then click on save. Okay, so we can just open our workshop folder, and there it is. So this contains our simulation files. So we can just right click and extract. Okay, so open the extracted folder and open up the NAMD. Okay, this is the prepared files that we're going to use for simulation. The most important thing is everything down somewhere. Yep, okay. So the important files is the step 3 input.pdb. This is the protein structure file. The step 3 input PSF. This is the structure file process for the molecular dynamic simulation. Then we have step 4 equilibration NMP. So this is instruction for energy minimization. And then step 5 production.imp. Okay, firstly we're going to prepare the step 4 equilibration files. So we've unpacked the .tgz file. We are now inside the NAMD folder. We're going to open the step 4 equilibration.inp file using Notepad++. Okay, for these settings, okay, step 4 equilibration.inp. So we're going to edit the .inp files like so. By default, the simulation is at 10,000 minimization steps. For practice, we just reduce it to 100. So go to the bottom, put a hash sign, shift 3 in these places, and then change this to 100. And we save it. Okay. Okay, now we're going to edit our step 5 production.imp. So these are the settings for running the molecular dynamic simulation. So by default, the simulation will run for 1 nanoseconds. So if you want to change to the simulation time to 10 nanoseconds, for example, we're going to adjust a few settings. Time step on line 110 and num step on line 147, the run step which is on the line 148, and we can use this formula of the simulation time in nanoseconds is equal to the number of steps times the number of time steps. So by default, usually the settings will be like this. And if you want to do in 10 nanosecond, usually we will manipulate the num step. And then in the simulation, we can take snapshots of the simulation process. The settings we can adjust to most on the right from line 14 to line 24. So the simplest would be to change every value to 25,000. So this would mean, for example, one snapshot will be taken for every 25,000 num step. So in 1 nanosecond, which equivalent to 1 million femtostep, so we divided that by the number of num step, 25,000, and we'll be getting 400 snapshots for that 1 nanosecond of simulation. But for practice, we're going to change the num step and run step to 1000, and we're going to change all of these settings here to 250. So let's do that. So we go for step 5 production.imp, we right click and we open it. So again, we're going to change the settings to num step and run step to 1000 and the city restart effect to 250. Right? So 250, 250, 250, 250 here. I've changed the settings in prior, so adjust this and also be adjusting this 1000, right? So then we're going to close it. So now we're ready to perform the molecular dynamic simulation. Okay, so now we're going to copy this command. Right click and copy. And then we're going to open the terminal from our NAMD folder. shift right click, put it as shell, we right click to paste the command, then click enter. So if this blinking means the process is running, so you can see the files are currently being created. Okay, so now the run is complete, as you can see here, and you can also view the files that have been created. Begin with step 4, and now we're going to continue with step 5. So I'm going to copy this command. If you're not using CUDA or NVIDIA graphic cards, you can use this particular command below. So right click, copy, and paste it again, and hit enter. Okay, so now the run is complete, as you can see here, and you can also view the files that have been created. Begin with step 4, and now we're going to continue with step 5. So I'm going to copy this command. If you're not using CUDA or NVIDIA graphic cards, you can use this particular command below. So right click, copy, and paste it again, and hit enter. Okay, so now our molecular dynamic simulation have completed. We're going to begin performing running post hoc analysis. So after we perform our simulation, we should have step 5 underscore production.dcd. So I have made a custom script of call directly auto. So I've kept it in the MD script folder, and we're going to move that file, or so we're going to copy that file to the NAMD folder, and then we're going to open the VMD using the PowerShell, and we open the TK console, and we're going to type source directly auto.tcl. So with this script, you should be getting the RMS data, hydrogen bonds, and solvent accessible surface area. So let's practice. Okay, so the process is complete. We can actually view the output, the log file here. Right click and activate Notepad. So this is the log file process going on. At the end, it will say the process completed. CPU time is actually telling us the number of seconds it takes to run the process, because we've shortened the process significantly. So yeah, it takes less than a minute, so that's good. Okay, so our simulation files is actually .dcd, it's this one. So we can view the files by accessing them using the terminal, or using Windows PowerShell. So type in VMD. Okay, so we can actually load our molecule here. So let's find. Okay, firstly we're going to load in the step 3 input.psf. Click open, click on load, and then going to browse again and find the .dcd. So I'm just going to use this function here, and yep, click on this and load again. So you can see this is our simulation. There's not much going on because you only have 4 frames. In reality, you're going to have a lot more frames because you'll be running it maybe 20 or 50 or 100 nanoseconds. Alright, so I'm going to show you what we can do with the analysis. I have the script that we can use. So go back to the Bioinfo workshop. and we look for MD scripts here. Open it. Now there's a file called reglateauto.tcl. Okay, let's just copy this one first. Right click, copy, and then we go back to the simulation folder. Okay, we paste it in the NAMD folder here. Right. So this script, I'll show you what it does. Okay, let's open it. Okay. So this script helps you to calculate the intermolecular hydrogen bonds between our ligand, our protein and our ligand. But we assume that the input file for the protein is called segname ProA, and for our ligand is segname HEADA. Usually when we submit our fast processing using CHARMM-GUI, by default the first protein will be segname ProA. Our first ligand should be segname HEADA. But if you have multiple ligand, they will be named HEADA, HEADB, HEADC, and so on. Similarly, for protein, if you have like a dimer, that will separate into segname ProA and ProB. So you can actually modify this, for example, by adding ProB. So it will start to calculate, factor in ProA, ProB as well in the calculation. However, you need to change every aspect of it. So instead of doing that, we're using the search function. I will show you how the content of the file. So this is the content. So this script is actually has been modified. So it will calculate the intermolecular hydrogen bonds, intermolecular hydrogen bonds, calculate the RMSD for the complex, and calculate the RMSD for the protein. It will calculate the RMSF similarly for the complex and also for the protein only. It will calculate the solvent accessible solvent accessible surface area. Again, it will calculate for the complex, the protein only, the ligand only, so that you can calculate the change in solvent accessible surface area. This will be useful. All of this will be useful when you are trying to study the behavior of your complex. And yep, so I will show you how we do this. So we bring back the VMD. Okay, from the extension, you go to TK console. Right. So you're going to type the command source, the name of the file, right click auto.tcl, click enter. Okay, so here's the output file. For example, let's see the receptor deity. So this is in table format. This is the frame number and this is the RMSD. To view the files better, you can use Microsoft Excel. So bring up your Excel file, you click and drag your file into here. So then you can click on the column, click on data, and let's expand this a bit. And go for text to column, delimited, keep it so, and then click on space. So you will separate the files so that into columns that you can process much more easily. So you can do something like this. So this is RMSD, so you can just type in RMSD on sample and put on 2D line or something like this, right? So you can change the time according to your the nanoseconds, because this is not the time in nanoseconds, this is the frame number. So you need to do some formula for you to determine the time on this particular part. Okay, let's close this. Don't save. Right. So these are the output that you will get, and this actually concludes our analysis. I will see you for the part 3 of the bioinformatics session, where I will go deeper into a more advanced analysis. Alright.